Adam Ward here. This is our second lecture on sort of our drag basics, or an introduction to drag. We talked a lot about friction drag in the last lecture video, and so in this one I want to talk to you about form drag. You'll recall that form drag was the term we're using to describe what happens when we get non-ideal behavior of our fluids, or we get that flow separation. And so we diagrammed this at the end of the previous lecture, and I want to show you a visualization of this to help you get a sense of what this actually looks like.
In our previous film, separation of flow from a boundary was treated as a purely geometric effect. A plate or orifice diaphragm, for example, is usually too thin for the flow to follow without an impossibly low pressure at the edge.
Okay. So what you're seeing on the screen here, and we'll just play this little video clip again while I narrate to you a touch. Think of that as like the top of that thin plate we looked at in the previous lecture. And as the fluid starts to move from left to right, you can see that swirl that's occurring on the downstream side of it. That's flow separation. So that fluid is coming around the plate, and then rather than coming back down in a symmetric way, you're getting this big turbulent recirculation. And the result of that is higher pressure on the upstream side of the plate and a net force that gets generated. So with that visualization in mind of what form drag and flow separation are actually about, let's talk a little bit about the effects of form drag at large scales. And so one of the areas that we're interested in this might be if we look at an airfoil or the wing of an airplane. And so two model results shown on the left-hand side. So in the top left image, what you're seeing is an airfoil that's tipped broadly how it would be when an airplane is flying. So there's really no form drag here. There's very little separation of the flow. And as a result, you don't get that turbulent recirculation over top of the wing. You keep a nice laminar boundary layer. You keep the fluid moving in an orderly fashion past the wing, and you generate a substantial amount of lift, shown in the green arrow. Now contrast that with the bottom panel, where you've taken that wing and you've tipped it so it's more perpendicular to the flow. And what you've done is cause a flow separation to occur right near the front of that wing, right? And as a result of that, you've got all of this big turbulent wake behind it, and you've minimized the amount of lift. Now, in an application like an airplane, minimizing lift is not a good thing, right? That's what causes us not to be able to get off the ground or to crash. And so this is one of the reasons that we want to make sure that there's active de-icing of our airplane wings. A lot of times on the front edge of an airplane wing, there's a de-icing mechanism that even as you're flying, it's basically bleeding a little bit of airplane fuel out the front of the wing to keep ice from forming on it, so you don't trip that boundary layer up and basically cut off your lift forces. Similarly, if you've ever heard of stalling an airplane, this is what happens when you take that airplane and you too quickly move that wing, or you get that wing at too steep of an angle. And what will happen when you'll be flying, and just when you hit that critical point, you get flow separation, and all of your lift that used to be keeping you afloat is suddenly lost into turbulence. And so you get this process of stalling an airplane. Okay. So this flow separation associated with form drag is actually really, really important to the way that objects will move through fluids. Pictured on the right-hand side here is a smooth sphere and a golf ball on the bottom half of the slide. And so the idea that we're trying to communicate here is, in the top image of that smooth sphere, the flow separation happens much, much earlier, so toward the front of the sphere, right? And because the flow separation happens way up there, you get a really thick wake behind the ball. That thick wake you could think of how big that wake is as proportional to how much form drag you're going to generate. So a really thick wake generates a really high form drag. And so yes, you might have a little less friction drag up on the front part of the ball, but in general that form drag is going to dominate the behavior. Now what we're trying to show on the bottom half is why golf balls have dimples. Okay? And the idea in the golf ball is that these little dimples, these little roughness elements on the golf ball, what they do is they actually cause the boundary layer to become turbulent sooner. And that turbulent boundary layer, for reasons we'll discuss in the next video, actually it adheres to the surface of the ball longer before it separates. So by controlling that boundary layer and tripping it up, you can actually generate a thinner wake, which means less form drag. Now, if you're a golfer, you care about that because you're putting energy into the golf ball when you hit it with a golf club, and then you want as much energy as possible to go toward the motion of the golf ball. You want to lose as little energy to friction and form drag as you can. And so minimizing form drag is a way to maximize how far a golf ball goes. And again, yes, you do have a larger region where that friction drag is going to occur, but as a general rule, for objects like this, the form drag is going to dominate the friction drag. One other application that you might have seen on a highway, so if we were looking down on a semi-truck, so here's a truck and they've got that large cargo box in the back. One of the things that we've started to see more and more are trucks that will have either a little cone on the back of them or they'll have some flaps that sort of flap out. And what those flaps are doing is taking the flow separation. So without the flaps, let's do this half and half. Without the flaps, you get separation that occurs right at the corner of the truck, and so you get a big form drag behind it. In contrast, in green here, with this flap in place, the flow adheres a little longer before it separates, and so you actually minimize form drag and you maximize your fuel efficiency by controlling where that separation occurs. One more example, again sports related, is the way that an object is going to move through the air. And so this was the Adidas ball shown at the top of the screen. This was a new design that Adidas came out with for the 2006 World Cup, and one that caused a lot of controversy. A traditional soccer ball has 32 panels. I think that this one was, 4, 8, 9, 10, was a 12 panel ball. And so it had a lot less seams on it and a lot more smooth, flat areas, right? And what happened was, by making a smoother soccer ball, you made it behave like the smooth ball, not like the golf ball. So the smoother that ball is, the larger that form drag will be. Now, who cares, right? Doesn't that mean it might slow it down a bit for a goalkeeper? It does have the effect of slowing it down, but what happens is not just that you have form drag, but it becomes unpredictable. So we've looked at, in this class, we've looked at the Tacoma Narrows Bridge and that sort of shedding of turbulent vortices that can impart forces on the ball. And so the same thing happens when this Teamgeist ball flies through the air. You get much earlier flow separation, and so you have this huge wake behind it. And so the shedding of those vortices actually causes the ball to move around. So if you're able to kick it with very little spin, which is actually a skill that a lot of footballers are practicing, and you can Google how to kick a knuckleball. What you're doing is basically generating a kick or a shot in which the random turbulent motion due to shedding of vortices is actually going to push the ball around. So it causes the ball not to go where the goalkeeper thinks it's going to be. For what it's worth, this is the exact same process that happens in baseball if you're going to throw a knuckleball. So in baseball, when you throw a knuckleball, what you're doing is you're trying to throw a ball that does not flick off your fingertips and rotate. Right? So a curveball, we purposefully impart rotation to make it bend. We talked about that in our last video. In a knuckleball, you try to throw it so that the ball is not spinning whatsoever. You want a ball that's just moving through the air with no rotation. And when that happens, you don't trip up the boundary layer. You get this massive form drag, and the shedding of those vortices pushes the baseball around in an unpredictable way. So that even a hitter who thinks they know where the ball is going to be can't predict what happens due to those random vortices. To give you a sense of what that looks like, let's look at a clip of a knuckleball slowed down to a point where you can actually watch it. You watch in this video for the seams of the ball. You'll actually be able to see that red stitching as it moves through the air and doesn't rotate.
Lazy boy say, I can hit that knuckleball. Here's another one. Get about 1.5 rotations on that. You know, you got to...
So we'll look at that one more time. Again, watch the seams. The ball does rotate, as the announcer says, about 1.5 times. But notice that neither the batter nor the catcher, who practices with this guy every day, neither of them can predict exactly where that knuckleball is going to be, because the random shedding of vortices pushes it around. So we can purposefully impart spin and control where a baseball goes, or a Flettner rotoship, with rotational motion. We can also purposefully avoid rotational motion or accidentally make too smooth of a soccer ball and create these random patterns. Now, for what it's worth, as a quick follow-up to this story, in more recent World Cup play, similar panel designs have been implemented, and so less panels, less stitching, the ball stays equally bouncy through the match. But soccer balls now have a roughness baked into them, almost the same way that a golf ball has. So the newest World Cup balls actually have a textured surface on them that will trip up that boundary layer and make the ball's flight more predictable, so that both kickers and goalkeepers have it's their skill, not random shedding of vortices, that cause the flight to move how it moves. Okay, so unpredictable flight if we get this large flow separation. We watch the video. The other area that you will have seen flow separation being controlled or taken advantage of is in cycling. And so in the top right panel, what you see is a cyclist who's actually in a wind tunnel. And so they're spending lots of time, effort, and money to design helmets, to design foam pads that are part of his uniform, to design wheels and frames that are going to minimize drag through streamlining. But you will have similarly seen riders taking advantage of form drag. So both in the picture of a rider right behind his crew car there, the Volvo in the top, and the pack of riders in the bottom, right? The goal there is to let the thing in front of you cut through and experience all of that boundary layer, and you tuck in the wake behind them. You tuck into their low pressure zone, and you actually get pulled along with that rider or that vehicle in front of you. Now, in competitive cycling, there are limits to how close you can be to your support vehicles and how long you can be behind them. But you'll certainly see teams keeping their best rider in sort of a second position, and somebody being in front of them to break the wind, and people behind them so that the flow separation occurs on the last rider, to keep that sort of champion rider in the middle of the pack and keep them with extra energy until the end of that leg of the race. All right, so we talked a little bit about friction drag. Now we've talked about flow separation and form drag. What we'll do in our final lecture is actually zoom in. These are kind of the macro effects. So what does it mean to a baseball, to a bike rider? What we're going to do in our last video is zoom into the boundary layer and actually look at what happens right where that fluid surface interface occurs. So stick with me, and I will see you back in a moment for that. Thanks all.